Possiamo passare al professor Kosterlitz se è in linea. Credo che fosse in linea 20 minuti fa.
Yeah, I'm here.
Good morning, Professor Kosterlitz.
Good morning.
Good morning.
At
Can you
least
hear us?
good
Can you hear
afternoon
me?
to you.
Very nice to see you. Professor Kosterlitz, let me briefly introduce you. Professor Kosterlitz was awarded the Nobel Prize in Physics in 2016 together with David Thouless and Duncan Haldane for discovering topological phase transition, topological phase of matter. Let me briefly explain in Italian, just in a few words, just a couple of words. Quindi le transizioni di fasi topologiche, la topologia, come Paolo Silvestrini mi suggeriva intelligentemente di spiegare, è quella scienza che si occupa di capire le proprietà degli oggetti indipendentemente dalle dimensioni e dalle forme. Quindi le transizioni scoperte dal professor Kosterlitz sono proprio transizioni di fase in cui c'è un cambiamento, un cambio di topologia. Professor Kosterlitz is very well known in the physics community for his study of two-dimensional quantum systems. These systems are very, very useful, in particular for quantum technologies and quantum computations. Professor Kosterlitz, thank you very much for joining us. The stage is yours.
Oh, thank you. I just have, let me say that my own interests and abilities lie really in classical physics because I don't understand quantum mechanics very well. So the problem for which I got well known is, of course, quantum mechanical, but the only bit of quantum mechanics we used was that the superfluid helium is described as bosonic, therefore it's described by a complex wave function, which can be regarded as a complex classical field, and we went from there. And so that's the origin of the, and then there's the question of why the two-dimensional superfluidity can be destroyed, because small fluctuations don't do anything. And then one has to go on to look at what actually destroys the superflow, which is the characteristic of a superfluid. And the only thing that can destroy a superflow are these more complicated objects called vortices. And so the problem came down to the statistical mechanics of an array of vortices. Now, of course, vortices are topological, but one doesn't have to think of it that way, because what's important for statistical mechanics are the important excitations, which one can argue are vortices. And so it turns out, of course, vortices are topological excitations. But for me, I was talking this with David Thouless, and I knew what vortices were, but Thouless suddenly said, "Oh, those are topological excitations," and I looked at him and said, "What's topology?" And that is about my knowledge of topology. So perhaps this is a bit encouraging to some of the audience, because you really, to do something significant in physics, you don't have to know too much. All you have to do is pick a problem, and if you have to be lucky, of course. But if you pick a problem which lots of very smart people have tried for a long time, and they're all spinning their wheels and doing exactly the same thing, not going anywhere, if you're lucky, you can come as the ignorant newcomer and look at the problem and say, why don't you try this? And if you're very lucky, this idea you have will work and you'll solve an important problem. Now, that's what happened to me, because I didn't know a thing about quantum mechanics except that the superfluidity is described by a basically a bosonic ground state, which is a complex field, and that's really the sole input of quantum mechanics we used. And so, as a message to the audience, who I presume many of you are students, at least I hope you are, the best way to go is to pick a problem and don't worry too much about what the problem involves, but pick a problem that you think you understand, and maybe with a bit of luck you'll be lucky and do something new. So I wish you all the best of luck in your endeavors, and I trust this conference is going well. And I'm sorry I can't be there in person. Unfortunately, at this time of year, I have to teach. I would love to be in Pompeii at this time of year, because it's cold here in Providence. But I guess that in Pompeii at this time of year it's not that cold. And since I've never been there before, I'd love to go and see the place. So thank you.
Thank you very much. Yeah, it's an opportunity for the organizers, maybe Paolo and Dino, to invite Professor Kosterlitz on the next possible occasion. He's never been in Pompeii, so it's it's a must. Pompeii, it's a must. You should see it. It's wonderful. It's amazing. Yeah, are there maybe a short question from the public? I think. Do you have any short question? I will translate it for you. Avete domande per il professor Kosterlitz? So I have a very short question, but I don't know, since you said that you don't understand quantum mechanics, I'm a little bit hesitant. I'm not sure I should ask you, because I'm sure I understand it less than you do. So the principle, my question is a naive question, maybe for a wide public. The principle of topology that underpin your Nobel Prize winning work, and that had an influence on the development of next generation quantum technologies. How do you think this will have an influence on, for instance, fault-tolerant quantum computers or topological qubits? There must be a level of understanding at which what you discovered should have an influence on topological qubits, on quantum computing, on error correction, fault-tolerant processes.
Well, I don't know too much about quantum computing, but it seems to me that the essential computing object with which one does computing has to be something very stable, because otherwise it's not very useful. And it seems that quantum, a small quantum system is not very stable to noise and so on, and therefore, of course, in quantum computing, errors are a big problem, and so error correction becomes an essential input. But if you have if your basic computing object is a more macroscopic object, you composed of many particles, it will be more stable, and maybe one can work with that without and not have to introduce this very complex error correction. Maybe not. So, but these topological objects, like, for example, vortices, they are definitely some macroscopic objects which involve a lot of particles, and they're not affected by minor impurities and faults. And then there are, I would guess that there are other topological objects, like, what are they called? Which might be useful in quantum computing, assuming that they're fast. Sorry, one can move them. They can move quickly. Of course, vortices are not very good for rapid manipulations because they're rather slow. So, it's basically a case of heads I win, tails you lose. I don't know whether these topological objects are actually useful for quantum computing, simply because they involve a lot of microscopic objects. That makes them stable, or relatively stable, but maybe they're not fast enough. I really don't know. I believe that in China they have a couple of quantum computers that actually function. At least I saw one in China, which is a rather impressive looking machine. And apparently it was actually working at the time. So presume these quantum computers are possible. I always thought that the whole idea of quantum computing was absurd, but it seems that people have got the working now. So
thank you very much. Thank you once again for being with us today.
Thank you. It was a pleasure.
And we hope to welcome here in Pompeii maybe in 1 or 2 years, as soon as possible
I hope
anyway.
So.
Goodbye.
Bye-bye.
Bye. Allora.